So let me, okay, just go back for a moment since people asked me. Okay, so two IID goods, we have 73%, okay? Two independent but not identically distributed, I showed you the proof of a half, but the actual result, the better result is 62 or 73%, okay? And now this, let's see if there is a, now I can jump over the proof. Ah, you see? It works. Okay, so what is G4? Okay? So assume that you are given a class of mechanisms. Now, when I say mechanism, it's always IC and IR. I mean, we don't think about something else. So let script N be a class of IC and IR mechanisms, okay? Let X be a family of valuations, okay? So distributions on RK plus, okay? Then we can talk about the guaranteed fraction of optimal revenue, which is, that's G4, guaranteed fraction of optimal revenue, okay? It's not half of G8, I'm sorry, for the economists. That's the most that you can guarantee with mechanisms in the class N. So it's the maximal fraction alpha, like 1/2, such that for every valuation in your class, there is a mechanism in the given class of mechanisms that gives you at least 1/2 of the optimal revenue. Okay? In computer science, they call it 1 over alpha approximation, and I'm sorry, I still don't understand it. 1 over alpha plus 1 over beta is 1 over alpha plus beta, or alpha plus, I don't know. But when you say 1/2, this guarantees 1/2, everybody understands. 1/2 of the optimal revenue, that's it. 50%. This mechanism, this class of mechanisms is 50% good. Well, it guarantees 50% of the optimal revenue. 25% is 25% of the optimal revenue. The benchmark should be the optimal revenue. Everything should be expressed as proportional to the optimal revenue.
That's what we do.
No, you do 1 over, which is, I'm always going to get confused. I know, I'm not going to, look, I am doing everything,
Alpha is in 0, 1, we do alpha, just like you.
No, like you said, what's square root n? I had to think, what's square root n approximation? What does the hell mean square root n approximation?
If it's 1 over.
Okay, that's my case. Okay, no, serious. When I saw that, I started thinking what, but whenever, look, okay, I'm doing everything against the grain in computer science. I know that, and
If that's your only concern, we are good.
Okay, good. I'm happy. Okay, now if you want a much more sophisticated definition, so you look at the most revenue you can get from any mechanism in N for X, divided by the most you can get from any revenue, from any mechanism. Script N is all mechanisms. And this ratio, you say, what's the minimum of that over all X? So that's the G4, okay? So if you say that G4 is 25%, that means in this class of valuations, now it could be all valuations, yes? It could be that you restrict yourself. In this class of valuations, such mechanisms always guarantee 25% of the revenue, maybe better, but at least 25%. Okay, so that's G4. So now let me translate the thing that I said before in a more palatable way. So separate, when you sell separately, okay? So we have two goods. IID means the class of valuations is IID. Two IID goods, that's the script X, okay? Then what we showed is G4, I mean that was the first element, I improved by the way. The G4 is at least 73%, okay? When we talk about independent goods, but not necessarily identically distributed, goes down to 62%. That's a square root E over square root E plus 1. That's one buyer, two goods, okay? Now, suppose, I said that I'm only going to talk about one buyer, but the 1/2 proof that I showed you, in fact, extends beautifully to n buyers. The same idea, with a little twist, okay? So, with a little, sorry, not a little twist, there is no twist there, it's straightforward. but a little more work.
So there's a 78% you mentioned as the
Wait, it's coming. Look, that's the order I did the slides, I'm sorry. But, no, but if I'm coming to it, I'm sure. But let me first do this. So, the proof that I showed you before the break, in fact, generalizes to a general decomposition, what I showed you, the diagonal, how you do, and then from two good mechanisms, you get a one good, and so on. So that turns out to neatly give you the same result when you have two goods and n independent buyers. Okay? You don't have to do much more work, it's the same. It's just there. Here, you see, I didn't have to wait much. Okay? The upper bound for all of those is 78%. Okay, so there is an example. Of course, the example is IAD, which covers this. One buyer IAD already gives you 78%. If I'm not mistaken, it's the equal revenue distribution. 2 IAD, equal revenue distribution. Equal revenue is that distribution where every price is the same. P times 1 minus P equals constant for all P, which says that FP is 1 minus 1 over P. That's a maximal distribution for which you get revenue constant. Say 1. Okay, now for this result, what's neat about this result, when you have implementation with n buyers, okay, question, how do the buyers behave? Are we talking about Bayes-Nash or are we talking about dominant strategy? The beauty of this is you don't care. So long as in the one good and the two good you do the same, the 50% holds. So if you want to compare what you get by separate selling to n independent players and n independent buyers versus what you get when you do optimally, if in both cases you use dominant strategy, 50%. You are guaranteed by separate selling at least 50%. If in both cases do dominant Nash, 50%. Okay? Again, it's this beautiful decomposition that is a general kind of, so that shows that it's quite powerful. Okay. That's all in Hassan.
Sergio?
Yes?
Separate selling a single item to many buyers, we know that the solution for Bayes-Nash is dominant strategy. Right? That's one.
But we don't know that. First of all, we don't know that for two goods. We know that because we know what the solution is.
Selling, if you sell one, what's separate selling? Separate selling is you
Each
sell
one,
this one
each
and if
good.
it's the only one, and this one is if it's the only one, right?
Yeah, right.
So sell this one as if it's the only one. That's dominant strategy, even if you.
That's a milestone.
Yeah. So when you
But
say.
you may
But the
say, but you may
benchmark, the
sell.
benchmark of rev is either the benchmark with Bayesian or with
No, but you said, he said use the same implementation.
Yeah,
for one
I
and
mean,
two
when you
goods.
look at G4 compares separate selling to optimal selling.
Yeah.
Okay? I'm saying in both cases, for the separate selling and for the optimal selling, use Bayes-Nash implementation. Or in both of them, use dominant strategy implementation.
But for separate selling, Bayes-Nash and dominant strategy give you the
But
same
the
revenue.
benchmark is different.
Why?
Yes, that's the result.
By the
Yeah,
milestone
that's what
result.
Myerson
You
says.
can implement it by
Nothing, you
milestone.
need to iron, it may be
But that's
different
only
number,
for
that's
one
no,
good.
that's
okay.
You may sell
No,
the
but
two goods
that-
to a single person.
No, because it is good separately. No, it's each good. No, he's right.
If
He's
you
right.
sell one good to n buyers, even if you want Bayes-Nash, the solution is dominant strategy. So I don't understand this statement.
Okay. Okay, I mean,
But in two goods, it might be different.
no, for two goods it's clearly
Two goods,
different.
yes, but
For
you
two
don't
goods
need
it's
to
clearly,
change the-
so what you're saying is that on the denominator, the benchmark is the same in both cases.
Yeah.
Okay, I mean, look, my view of n goods is that my co-authors always want n goods, and I said, I do not understand one good is already too much for me, and I don't care about sorry. I don't understand one buyer. N buyers, it's too much for me. I want to understand one buyer. Now, you give me results that you get it for free, okay, we can put it in the paper. So I never cared about n buyers. I see now that I should have cared more.
There's another thing I don't understand. I mean, when you have a large number of buyers,
Yeah. Yeah, but large number of buyers when you sell separately, same large number of buyers when you say two goods. It's the same. Say n is fixed.
each good, you're getting, the buyers, what's the relate? They are the same buyers, aren't IID buyers?
No, I said independent, not identical.
They are not IID?
No, they're different valuations. So each
So
one
if
go,
they were I and B, then we know.
if I D, yes, that's trivial. Okay. Okay, now, at the request of everybody, what happens when you drop independence, okay? So now we take two goods and arbitrary dependence between the two goods. One buyer, we are back to, n buyer was parenthesis, okay? I shouldn't get into that, okay? So we are back to two goods, one buyer. One seller, one buyer, two goods, but now there is some correlation, arbitrary correlation between valuation of good one and valuation of good two, okay? What's G4? So we got lower bound of on independent of 62%, right? So how much do you think is going to go down? Only those who don't know should reply, okay? Will it go down to 50% or will it be lower? Okay. So separate selling, that's what we are talking about. Answer is 0. 0. So let me explain what I mean.
Isn't it implied by what you said about when you increase the willingness to pay, then you lose arbitrary money?
No. Oh, sorry. If you knew that, but that is going to be a consequence of what I show you now. So that slide was something I said, see later. Now you cannot use something where I say see later to prove something that you see now. That's not allowed. Sorry, no. What I mean, the proof of that will come in a few slides from now, based on what I'm telling you now. So that thing is. So I'm lucky. I almost didn't have that see later then, but now I see it's very important. But good observation. Okay. So what do I mean? Let me be very precise, so you don't think I'm yes. Give me an epsilon. Okay. I can find the valuation in 0, 1 squared. I mean, I don't need anything unbounded, yes? It has nothing to do with having bounded value, such that the separate revenue you get from X, so that's the revenue of X1 plus revenue of X2, S rev is the sum, yeah? Is less than epsilon of the optimal revenue. Selling separately gives you nothing. There are valuations, okay, on two goods, so that if you sell them separately, you are getting arbitrarily small proportion of the optimal revenue. You're getting nothing, okay? So separate selling, which gave us 50%, or in fact 62% in the independent case, gives us nothing in the dependent case, okay? Okay, so separate selling is bad, okay. Let's try bundling. We saw that bundling usually is better, many times is better. So what's G4 for bundling? 0. Okay. For every epsilon, there is some valuation, so that bounded, so that selling the bundle gives you nothing, gives you epsilon fraction of the optimal revenue. Now you'll say, okay, wait a minute. Maybe for some, bundling is good. For the others, the separate is good, but there is always one of them may be bad. In fact, Moshe and what are your co-authors? I forgot. Nicole, yeah. As a nice result, again, I only showed you here two goods. So I should say in parentheses there is a lot of work on what happens with K goods and how the bounds dependent on K. So you get some bounds like 1 over K, 1 over log K, 1 over log K, I don't know, log K over K, various functions of K. Question is, can you get some, and usually many of those go to 0 as K goes to infinity. Question, can you get some things which are independent, constant in K? So Moshe has a nice work where he gets 1/6, right? Bound of 1/6, which by now is better. There is something better than 1/6.
5.2 is okay.
You mean 1 over 5.2? Okay. So so you know what? Let's now look at separate selling, at bundle selling, at all deterministic mechanisms. Now what are deterministic mechanisms? Deterministic mechanisms are, again, allocation. You either get the whole good or nothing. So the number of possible allocations is 2 to the power k, right? Which subset of goods you are getting, and there is a price for each subset of goods. That's a deterministic mechanism. You can get nothing for 0, of course, and any other subset of goods, there is a certain price for it. There's a certain payment that you have to pay. That's the deterministic mechanism. Includes in particular separate selling that only allows to get one good at a time, or bundle that only allows you to get a big bundle. Okay? So that's the deterministic mechanism. What's G4 for deterministic mechanism? Well, you guessed it, 0. Okay? So there are valuations, okay? Such that bounded in 0, 1 squared, okay? Such that every deterministic mechanism is giving you less than epsilon of the optimal revenue. Gives you nothing. All deterministic mechanisms give you nothing. That's quite stunning, yes? Okay? Now, the same of Holt. Now, once it's 2 for 2, it's true for anything more. This result for k greater or equals 3 was obtained by Briest et al. And then Noam and I obtained it for k equal 2. There is a general there is in fact an explicit construction. I can tell you what that random variable looks like. I can tell you exactly. Here are the values. Here are the probabilities. It sits on a nice curve that I can tell you exactly what it is. It comes from, in a sense, developing some formula. Okay, never mind. There is some work to be done there. Or there can be a general construction saying there exists a partition and so on, where you start counting things. So there are 2 separate proofs. Our joint papers have many results with 2 proofs, because there are 2 authors, and the 2 authors have different types of proofs. But that's useful, because sometimes you can generalize proof 1, sometimes you can generalize proof 2. But that's always nice. Okay. Okay, now I come to your question. Okay? So I'm still with k goods and arbitrary dependence. Now, remember the guaranteed revenue. What was the guaranteed revenue? How much you can guarantee, sorry, it's defined first by what's the worst revenue that you can get if x is just a lower bound on the valuation. So you are given x, you don't think of x as the actual valuation, but think of x as being a lower bound of the actual valuation, so the valuation could be x or higher. And then you ask yourself, okay, what's the revenue I get from any y that is higher than x, and what's the worst? Okay? And that's this infimum. And if you remember, I remind you, I'm sure you don't remember, but there was a result there saying this can be guaranteed. That's why we call it GREV, guaranteed revenue. Yeah.
X is a distribution.
Yeah.
And what is
No, x is a random variable,
X is a random.
which means for every small omega, you get a value. Now, instead of getting that value, you get a higher value. That's exactly first order stochastic dominance. Now, if you don't like, greater equal means for you, if you want point-wise increased values, or if you want first order stochastic dominance, it's exactly the same thing.
Okay.
Okay? So x is just a lower bound on the valuations. Valuations could be higher. And you ask, what's the worst revenue? How much worse the revenue could be? Okay? So if the valuations go higher, how much revenue could go down? And what I showed, by the way, that this is, you can guarantee it. There is one mechanism that you can use, and then no matter what y is, you are going to get at least this number. So there is, you can, because in principle, for every y bigger than x, there is a different optimal mechanism. Minimax theorem says no, there is one mechanism that if the seller uses it, or if it is used, no matter what the valuation is, the revenue is going to be at least this much. And that's the most you can guarantee, of course, because that's infinite. Okay? Okay. Now, question is, how much smaller this can be than the revenue of x? What's G4? What is G4 of GREV? What fraction of the optimal revenue can this infimum be? If this is small, that means that non-monotonicity is a problematic issue. It means that if y is bigger, you can suddenly lose all revenue. Okay? Okay. So here, I'm not going to tell you the result, I'm just going to prove it to you. It's a simple proof. I only show simple proofs. Okay? Let z be the sum of the xi. It's a one-dimensional random variable. Okay? Okay? Now, x, which is x1, x2 up to xk, is less or equal than z, right? Because x1 is less than the sum. They are all non-negative, yes? So x1 is less than the sum, and x2 is less than the sum, and xk is less than the sum, right? So if you look at the valuation, that is z for good 1, z for good 2, z for good k, then it's a higher valuation than x. Okay? Which means that the worst, the GREV of x, which is the worst that can happen, is less than the revenue of ZZZ. Because that's one of the instances here of y bigger than x. If the valuation of the buyer is not x, but rather ZZZZ, which is bigger than x, then you can get no more than that. So GREV is at most this, right? I'm saying trivial things. If you don't follow, then you have to follow. Those are, I mean, again, you are not going to follow why GREV is 0 for 2. That's, you know, that takes, yeah. But what I show you, believe me, you should follow. Okay. Huh? You have to follow. Huh? Okay, now, what is rev of, now, ZZZ is a valuation, ZZZ is a valuation that lives on the diagonal. There is a probability distribution on the diagonal, right? That's what ZZZ means, okay? And now, that means it's a one-dimensional problem, where essentially you are getting points there, you are getting 7, 7, 7, 7 with some probability, 8, 8, 8, 8, 8 with some probability, and so on. I claim that the revenue of that is exactly k times the revenue from Z, because you get whatever mechanism you are using for Z, okay, you can replicate it and say, okay, you are getting, again, I'm not even using the Meyerson theorem. I take the one-dimensional mechanism and say, same mechanism you are applying to all goods. You are getting Q and paying S. Now you are getting Q, 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 and paying K times S. Okay?
Sergio, isn't
Yes?
everything that you've said so far applies also if you take Z to be the max?
Yes. But
Don't
then,
you get better results?
no, I'll reply to it. Hold it, hold it,
Okay.
hold it. Yeah, the answer is yes, yes, but then I need one more line. Okay? But let's just finish that. Now, what's the revenue of Z? That's the revenue of the sum. It's B rev, right? Revenue of Z, it's a revenue of the sum. It's what you get from the sum of the xi. So what did we get? The G rev is less than K times B rev. Now we know that there is X such that B rev gives you epsilon of the optimal revenue. Well, now you are going to get K times epsilon of the optimal revenue, which for all practical purposes is S epsilon as the other one, is S0 as the other one. So conclusion, G4 of G rev is 0. Okay? Which again, just shows you that this non-monotonicity is not a marginal phenomenon. It's a very significant phenomenon. Okay? If the valuations of the buyer go up, you may end up with no revenue at all, with an absolutely small fraction of the original optimal revenue. What can you do against it? I don't know. I have no idea. Okay? And as I said, it appears that the game is not a zero-sum game. Okay? The fact that the seller gets less does not mean that the buyer gets more, because the allocation changes. Okay? But in fact, I think that one might be able, again, I don't know, Jan and I started thinking about it. At least in some examples, it seems that it's worthwhile for the buyer to do that. It makes the revenue of the seller much smaller, and he gains. Okay? Yeah.
Yeah, so the definition GREF is that there exists such an X, not that for all X.
Yeah, G4 always says the worst case.
Yes.
This is always worst case. So when I say, no, this is defined for every X.
Right.
G4 has the
yeah.
infimum over X.
Yeah.
It says, of course, there are X's for which, you know, rev and G-rev are the same. For example, if the optimal mechanism is monotonic, then G-rev and rev are the same. If the optimal mechanism is monotonic, then if Y increases, the revenue can only go up. Okay? In fact, for almost all examples, we know everything works beautifully. Yes, but, you know, there are examples where it doesn't. Yes?
Can we design a distributional robust mechanism? I mean, if we know the potential, the set of possible random variables X, can we just design distribute robust mechanism? I mean, just the min max. The first min taking over our potential random variable distribution. The second max over mechanism.
Yeah.
Can we then just resolve this issue by design this kind, solve this kind of problem?
No, because, again, those distributions, now it's true, they are not things you meet in the street every day. The ones where you get epsilon of the revenue. Yes,
Yes, I know. But I mean, if we know the status, so if we know the X belongs to some
Yeah,
definition.
so if it belongs to the bad set of distributions, what can you do? You are given that distribution from which the revenue is 7, okay? But you know that if in fact the willingness to pay of the buyer increases, you're going to end up with 0. What can you do? You tell me. I mean, formally you can define whatever you want, but tell me some procedure by which the seller can avoid getting less. As I said, it's in the interest of the buyer to do that. It may be, sorry, I have to quantify it. It may be in the interest of the buyer to even commit himself to a higher valuation. In the end, he's going to get more, seller is going to get less. What can you do against it? I don't know. I have no idea. Yes.
What if, so there is some literature about what's called, I think, buy many mechanisms,
Yeah.
which is about restricting the payment to be sub-additive, I believe.
Yeah.
Would that help you?
No. You have a different answer?
Yeah, no, yeah, it's
Huh?
sub-additive. I mean, if you're comparing to sub-additive,
Yeah.
then you're doing well, right? It's not zero.
Oh, you want the benchmark to be,
Benchmark.
oh, you want the benchmark to be what you get
The
from
best-
sub-additive,
Yes, the best
from
sub-additive.
whatever, sub-modular or whatever class of, well, if you restrict yourself, sorry, okay, let me give you a better answer. Restrict yourself to monotonic mechanisms. Problem solved. G red equals red.
Yeah, but that's a
No, I
pretty
mean,
harsh
now,
restriction.
okay, why is by many more reasonable than,
So I think there is actually motivation for buy many,
Yeah.
because you don't want people to be able to manipulate in the sense that they are better off buying X separately and Y separately than the bundle, so you don't want the pricing.
okay. My answer to that is bullshit. This is bullshit story.
No,
Because
no,
the
no.
story, no. You are changing
You
the rules
go
of the
to
game.
a
The
restaurant.
no. Let me make a point. I want to make a point. The rule of the game is
You
tell-
already made a point.
No, I haven't yet. No, sorry. I made it more force. Okay. Remember the revelation principle says, take a mechanism, whatever you want. You tell me the rules of the game. You want to go twice? You go twice. You want to go on 1 foot? Go on 1 foot. I don't care. You tell me all the rules of the game. Once you tell me the rules of the game, I look at the direct mechanism. The direct mechanism translates the rules of the game into a menu from which you choose one and one only. Now, after I do that, you say, no. Now you can choose 2. That means your mechanism is a different one, so the direct mechanism is something else.
Yeah, the
So
direct
you can't-
mechanism has sub-additivity property, because you look at the menu and they're like, why is the restaurant selling 2 things separately? This is
Because it's a direct mechanism already. Because if that was possible, you'd start with a mechanism that is already something like that. But once you are given a direct
But
mechanism,
I would like to claim that restricting the agent to choose one entry in the menu is the unreasonable thing to do.
no. But then you didn't get the point I made. This is not a restriction. This is a translation after. So allow him to choose, give a menu. Allow him to choose twice, 3 times, 7 times, do whatever he wants. Once you do that, translate this to a direct mechanism. That will be a different menu now.
Yes.
And in a different menu, you only choose once. You only choose one entry.
But now it's restricted.
I
Now
don't
the
care.
menu is
Okay,
restricted.
but okay. So you're talking about a different class of menus.
Yes,
Okay,
which I think makes some sense.
sure, makes sense. But look, if you restrict, as I said, restricting the, if you don't talk about the optimal revenue, but the restricted optimal revenue, which means let's restrict to a different class of, to a subset of mechanisms, then of course, all these things change. Okay? In particular, I gave you immediately,
The monotone.
if you say, I only look at monotone mechanisms because non-monotone mechanisms I don't understand. They are crazy. Nobody should use them. I don't care what. Then this problem disappears. Okay? You want to look at some modular ones? Sure. I mean, there are lots of classes and yeah. So, okay, no, but I have a problem when people take the direct mechanism and then say on top of, now you can start manipulating it. That's a no-no. Okay. That's modeling. Now, you asked me, what I could put here maximum. I could define W to be the maximum of the xi, that will also work. Now, what's the revenue of the maximum relative to, what's the revenue of the maximum of x1 up to xk? You know what it is?
It's No, but I think the question does not make sense because this
Oh,
already gives you zero.
I know,
so-
but wait, no, but it's a side. You asked the question. Now I ask you.
Can I take it back?
No, because the answer is okay. The answer is that the maximum is less or equal than SREM. Exercise, an easy exercise. It's really an easy exercise. But you know,
Okay,
first
so
time we
it
looked
gives
at
you
it,
the same answer for
so
a different,
you are just going to
regression.
get here. In fact, the GREV is less or equal K times SREM.
That's right.
So it's
And
less or
the
equal
same
than
zero.
not the maximum, but the minimum of SREV and BREV. Okay, so it's again, okay, very good.
Okay, so that's actually another result, we can say, that G
Rev is less or equal than K
the
times
minimum
SREV. Yes.
of B rev
And if you
SREV.
want, you can also do, you can now improve, take bundles, divide into bundles, and each bundle sell the bundle, and then take the sum of the revenues from bundle 1 plus bundle 2
Okay.
plus bundle 3. You can start playing lots of games like this, and but they are all telling you that once you look at the relative to the optimal revenue, the loss here due to non-motonicity could be arbitrarily large. Okay, so now you can start using it. Okay. Yeah, you see that's new. Okay. Oh, here is a slide again, which we'll see later, and now I dropped the we'll see later. We just saw it. Okay, and as I say, I'm still bothered by the fact that I don't know how to overcome it. I don't know how the seller can overcome it. There is, cannot tie his hands in some way or do something. There should be some clever thing. But I think there should be a theorem saying there is nothing he can do. But still, there is still a question mark here. Okay, now, okay, final thing again. Probably will end sooner than you'll get some break before the reception. So I want to talk about menu size. Okay, so I'll tell you why we want to look at that. But for the moment, let's look at that. Let's assume that instead of looking at all mechanisms, we are only looking at mechanisms that have 10 choices. You don't get a mechanism where you have 1,000 choices. Who can see a menu of size 1,000? You go into a restaurant where it takes you half an hour just to go through the menu. I don't like those restaurants. Yeah. But also for other reasons. If you can prepare everything, probably nothing is good. But that's a different story. They can do chicken, and they can do fish, and they can do that, and that, and that, and that, and that. Probably nothing is above average. So you want a restaurant that specializes in some things that are good. And there can be too many.
So you violate warp.
I know. You know the story about Schmeidler, right?
No.
But I'll tell you. Never mind. So, assume that we are looking, a mechanism has menu. What is I didn't define, yes. A mechanism, what's a mechanism? For every valuation x, I have qx as x. That's the outcome at x. And I can look how many different outcomes there are. Namely, what is the size of the menu from which I have to choose one? Okay, that's the direct mechanism, is the menu and I have to choose one. And of course, the bigger the menu, the more choices are, the buyer likes it better. Yes, because he has more choices, his payoff can only go up. Okay? Question is, suppose I'm saying, you know what? For example, you can only buy the bundle. That's menu of size 1. You have only one choice. 0 doesn't count. You always can do nothing. So I'm only counting the real choices. So the menu size is how many options you have except 0. So bundling, the bundled revenue is menu size 1. Okay? Here's another result. Suppose now I tell you, no, not, so, sorry, let's go back here, I jumped, okay. So we said that bundling, G4 is 0. You get 0 fraction of the optimal revenue. Separate, 0 fraction of the optimal revenue. Deterministic, 0 fraction of optimal revenue, okay? Now I'm telling you, you know what? Not bundling, not separate, not deterministic, but I give you just 100 options. They can include lotteries, I don't care, some 100 options. Cleverly chosen 100 options. How much can you get? The answer still, the answer G4 is still 0. Okay? So if I limit ahead of time the number of options in the menu, then there are distributions, there are valuations for which the optimal revenue from all mechanisms that employ only M menu entries or less is no more than epsilon of the optimal revenue. Okay? Now, what happens when M, in fact, I think I have a better slide. Okay, I'll show you that. Okay. What happens when M increases? When M increases, clearly you can obtain more, because what you can obtain with menu of size 7, when you have size 8, of course, you can only get better. You have more mechanisms that you can use. Okay? It turns out that the increase is polynomial. I forgot exactly what, I think I have a slide that I'll show you. Now, you know what, I want to show you, sorry, I have a better slide. I have a better slide. Okay. So MREV, maximum revenue, overall mechanism with most M choices. Okay, so let's go slowly. Suppose you have only one, menu of size 1, you have only one choice. One possibility is BREV, bundle. Turns out that's the best. If you have only one choice, sell the bundle. That's the best you can do. Okay? Why? You want a proof? Here I'll give you a proof. Because whatever it was some Q1, Q2 up to QK, and paying S. Well, give to the buyer 111, and he still pays S. The buyer will still get it, because you only increased his allocation, and he still pays the same, so he'll still happily get it. So you can get the same S from pricing the bundle. Okay, end of proof. More interesting, if you allow menu of size M, then you get no more than n times BREV. Okay, each menu entry can get you at most BREV, essentially. Not, I mean, I'm not saying it right, but that's roughly the intuition. Okay, again, the proof is quite trivial. This is more complex, but again, that's computer science kind of thing. It says that it increases by at most m, and at least m to the power 1/7. 1/7 is not tight in any way, but just shows you that it increases polynomially with n. Okay? So there are x's, of course. There are x's where BREV is already optimal. Okay? So this is a lower bound, some x, for which this happens. Not all x. All these are for all x. Okay? Now, look at deterministic mechanism. Deterministic mechanisms have menu size 2 to the power k minus 1. Okay, let's ignore the minus 1. Okay? Because there are a number of possible allocations are all subsets of k. So there are 2 to the power k. So DREV is clearly less than what you can get when you restrict the menu size 2 to the power k. Okay? That's true for all x. The opposite inequality says there are x's for which you get essentially 2 to the power k over k of BREV, which is 1 rev. Okay? So what it says is that DREV is essentially like mechanism with revenue size 2 to the power k, which says that the fact that you don't succeed in getting anything from deterministic mechanism has nothing to do, well, has a lot to do, but can be viewed as coming not because we restrict mechanisms to have all the Q's 0 or 1, but because by being deterministic, it restricts the menu size to 2 to the power k. That's the real reason that deterministic mechanisms are unsuccessful. The reason that BREV and DREV and BREV and SREV, all of those are unsuccessful in getting a big proportion of the optimal revenue is because they are limited in how many options they can provide. And indeed, the examples where you can get a big revenue is that we have a huge number of entries, and each one has its own tailored menu entry. And from each one you get something, but he has its own menu entry. You have to carefully make them, so you need a lot of menu entries in order to get a lot of revenue. And when you are limited in the number of menu entries, like all the simple mechanisms are, then you are in trouble. then you can get only a small fraction of the optimal revenue. Okay? So, menu size is in fact one way to measure the complexity of mechanisms. The bigger the menu size, the more complex the mechanism. It's a very simple, extremely simple measure, but it captures something very nice relative to the revenue. Because it tells you that again, if you look at the revenue for mechanisms with complexity, menu complexity m, you get at most an increase of factor of m in revenue. So the revenue increases linearly in the menu size as a complexity measure. Okay? Now there are other complexity measures, and you are going to talk about it, am I? No?
About what?
Complexity measure, something.
I'm going to talk about sample complexity.
Okay,
That's
so
different.
yeah. So you'll see other ways, but that's a very simple way and quite powerful. Okay. Okay. That was the extra slide that was missing. Let's go back. Oh, I see here M. I see notation has changed. That was an old slide. Okay. So M rev M and the M rev M, the previous one are the same. There were two different notations. Never mind. Okay. Okay. So here's a summary on G4. The guaranteed fraction of optimal revenue of simple mechanisms. Now again. What's a simple mechanism? Well, look, a mechanism that has a zillion menu entries cannot be simple. I mean, if the buyer has to start thinking about the zillion menu entries and start doing optimization, it can't be simple. We can't describe it easy. Well, sometimes you can, there is an issue. But in principle, simple mechanisms are mechanisms that can't have a big menu. And essentially what we have shown is that simple mechanisms have a very bad guaranteed fraction of optimal revenue. They may yield a very small, essentially zero G4. Okay? So, this is a summary of what we know. Again, it's the same thing. For in IAD 73%, independent 62, correlated 0. Okay? That's really a dramatic jump. And I think I'm finishing much earlier than I thought. So, so the summary of what we saw, I thought it was going to take more time, but okay. Maximizing revenue with multiple goods. So many of the results that we have for one good are false for multiple goods. Extremely complex problem, even when you take very simple distributions, as I said. What you've learned from one good is too good to be true for two goods or more. And simple mechanisms may not. But in some cases, they may give good uniform approximations, in some cases not. And again, there is huge literature following all this. And
What do you think the uniform approximation?
uniform for all x, or for a big class of x, that's what I mean. Not for one x, yes, what I mean is for a class. Yeah? You have 1/2, 62%, that's a uniform. That's over all independent or IAD thing. That's what they call a uniform bound.
General one.
General, okay. Yeah, because for every x you have a different bound. But that, okay, maybe the word uniform is too strong. Too strong. Okay. And again, I didn't talk at all about the dependence on k. How do those bounds change with k, which again is an interesting issue. And I think that's my last slide. So thank you. Now, if you have questions, I'm here, and now, later, whatever. Yeah.
So conceptually, if we have risk-neutral agents,
Yeah.
why do we care about the guarantee? Like, are risk losing or not getting the seller?
No, guarantee is on the expectation. It's on the expected payoff. Everything talks about expected payoff to seller, expected revenue. So the risk neutrality comes when you compute expectations in the, you take expectations. You don't have to apply a utility function, some concave utility function on top of it. That's all. Now, in principle, you could do that, as I said, even for one good. Even for one good. If, say, the seller has now some, he doesn't get S, he gets U of S. He gets money, but he has utility of money, and that's translated as some concave function U. Then the Myerson result that says there is an optimal mechanism with a unique deterministic unique price, that's false. Okay, you are getting a continuum of prices. You are getting a continuum of outcomes. Okay, so even for one buyer, one seller, one good already. Once you introduce a little risk aversion, then the whole thing becomes another layer of complexity.
Yeah, okay, no, that's, yeah, that was my confusion. But also, don't we know the distribution, like as a seller?
Sorry?
Like, guarantees are for, like, there exists distribution when mechanism fails, right?
Yeah.
But don't we know, like Myerson assumes we know, right, the distribution.
No, the optimal mechanism
Yeah.
is a function of a given distribution. You give me the distribution, I'll tell you what the optimal mechanism is. Okay? Are you talking about the guaranteed revenue, the GREV, or what are you talking about? Or
I'm just confused, like, this current G4, right, it's about different distributions, but we can tailor to each specific distribution, find out some mechanism where
No,
next
so
mechanism
what,
is not
okay,
zero.
so forget G4. Forget G4. Here is the statement.
Yeah.
There exists, okay, no, G4 is an elegant way to state something, okay, in a uniform manner. Forget G4. Here is a claim. There is a distribution. There is a random variable X, a distribution of valuations in R2. You know what? In 0, 1 square, in the square, not anything fancy, okay? I can give it to you. In fact, you look in the paper, it's explicit. There is one which is explicitly given there. Tells you values and probabilities, okay? Such that no simple mechanisms, not bundled, not separate, not an intermistic mechanism, not an intermistic which has 10,000 entries, can give you anything than an arbitrarily small proportion of the optimal element. The optimal, in fact, let me put it this way, make it more extreme. If you don't want me to talk about, if you allow me to talk about unbounded distributions, the revenue is infinite. Anything anything else gives you only one in revenue. Okay, BREV, DREV, MREV, all of them only give you one. But the revenue is infinite. The optimal revenue is infinite, and with simple mechanism you can only get one. For a specific X, one specific X, here is a distribution in front of your eyes.
But
Okay?
if we're not in simple, I mean, then we
Not simple is because you need an infinity many entries in the menu.
Okay.
Or arbitrarily large again, if you do it with epsilon. So I don't know what's more convincing. Some people like infinity versus one. I like epsilon and bounded. Sounds more palatable because once you go to infinity, you start being, where are they cheating me? But if I tell you it's in 0, 1 square, 0, 1 square, okay, here are the points, here are the points. 0, 100 square, if you have problems seeing, I can do it in 0, 100 square. Yeah. Again, everything is homogeneous here, so multiplying values by 7, it's ratios, doesn't matter, okay? 0, 1 square, here is a distribution, and here is the optimal revenue, and this is what you can get by any simple mechanism, which is nothing, epsilon of the optimal revenue.
Does simple have a definition?
Yeah, so the definition I proposed here is that simple is bounded by some n.
Okay.
That's a proposal of a definition of what simple means, bounded by some n. 1,000. Mechanism with menu size less than 1,000. More than 1,000, I hardly can think of that. Okay? They can get to nothing. I don't care what those 1,000 will be. Lotteries, subsets, whatever, anything you want. Okay? Cannot get anything. There are distributions where you get nothing. Yeah.
Mr. Malik,
Ah,
what's the connection between simplicity and the revelation principle? Like, could it be that like a mechanism with indirect representation is simple, but when we apply the revelation principle, we get something which is arbitrarily large?
yeah, so you say, maybe there is a representation of the mechanism that is concise, is compact. When you go to the direct mechanism, you get zillions of, like for example, I could tell you a mechanism for one good, or say, for example, you can get any price that is a multiple of 1 over 1,000 for any allocation that is a
Allocation X, plus X.
price, something like that. I can give you a simple function from allocation to that, and right. So I don't know how to measure that. Yes. So that's I don't say this is a universal measure of complexity, because there may be simple things. And again, if you start using calculus, then you do optimization over a continuum of options, and on this I don't have an answer. Right. But again, it all started from simple mechanisms that we know about, separate, bundling, deterministic. Those are natural. They are not just simple, they are natural.
Yes.
And the question is, we want to embed them in something which preserves the simplicity and keeps all these natural ones, and the one we thought of is the menu size. But there are other ways, definitely, and going from the extensive form to the normal form indeed may increase complexity by each factor. You're right.
A quick clarification question. So in the whole, so when you say there exists an X such that optimal is infinite and simple is finite, so, and when we start talking about a finite M, it's that there exists an X such that for any finite M, the revenue is finite, or like for every M there exists an X.
So, let me be, the answer is this. Let's talk one rep. M equals 1, that's B rep.
Yeah.
First of all, I find something which is, for which B rep over rep is the smallest you want, is epsilon.
Okay, good.
And then
Then
M,
any M-
you get M times epsilon. I
Yes.
tell you exactly the answer,
Sounds good.
okay?
Yeah.
Yeah.
Can you say something about distributions for which we get a good approximation with simple mathematics?
Well, independent, you saw, if 1/2 is good, then, that's good. Do I know about other things?
I mean, if you are happy with finite, Moshe and I and Noam have a paper on 99% revenue
For-
for additive bidders.
What do you see
And
there?
unit demand.
Independent.
Independent.
But still independent.
But
It's
still independent. Yeah,
So
yeah,
you can improve,
independent.
yes,
Because
you can improve the 50,
I'm just
62%
saying you
or
can improve the
whatever.
50 to
Yeah,
99.
yeah.
Yeah.
So as I said, this is, I cannot follow this literature. Okay, I'm sorry.
Because you did typing.
Huh? No, it's, so I only gave you the start and the ideas. Now you,
But is there some property which is maybe weaker than independence that can guarantee something?
I don't know. Yeah, so there, at the time, I think there was some thought about whether there is positive or negative correlation between X1 and X2 in those counterexamples. Now, it's true that there they increase together, but I don't think anybody did. Did anybody do? You should know.
Matt Weinberg had something about specific forms of correlation.
Between X1 and X2, between, say, let's talk 2.
So, no? You had this rectangle
Yeah.
function.
Oh, so that is
that
about
was-
smooth analysis. So if you do, it's about perturbing the thing, like,
Oh, I think you're right. It was
yeah, it was
smoothness
smooth analysis. So it's basically if you take the bad example from
But again, careful. Correlation 1 means on the diagonal. That's a one-dimensional problem. That I know how to solve. Grev is 1. Okay. G4 is 1. Okay, no problem. Okay? If you are, that's correlation 1 up to linear transformation, which doesn't matter, you are on the diagonal. That's a one-dimensional problem. Then you can, then it's one dimension, you know exactly what you get. Okay? No, wait.
Something else.
If you take correlation which is close to 1, that means in some sense you're close to the diagonal. With high probability, that is, you can't be too far away. When this is 7, no, it says the expectation should be, no, it doesn't say that, no, it does not say that, it says expectation of y should be close to no, I was going to say something false. No, I don't know, sorry. No. Independent is correlation 0. So correlation 0 we know, correlation 1 we know. When we are in the middle, I have no clue. That's the best answer I can give. And it's not clear that correlation will help you or something else. I mean, you could talk about measures that look at your distribution, and look at the support and how big, what you can put it, if you can constrain the support in some sense to some nice sets. I don't know. It's still.
So maybe like finance, like something with the finance of the support can say something about the many complexity.
Well, sure.
Right?
If
So
support is of size, support
So
is of
that's-
size 100,
that's
many of
trivial,
size
right?
100 suffices because the linear programming, that's what it does. Okay?
Yeah, but that,
Whether, now if I give you arbitrary support of size 100, you will need 100 in the optimal mechanism. If sometime you can work with less, it could be, but I don't know if you can. As I said, those things are, in one dimension, everything is monotonic. X goes up, Q goes up, S goes up, everything goes up. I mean, things are behaving like, if from here to here everything is okay, then from here to here everything is okay because you do it step by step.
So
In
try
two
to say
dimensions,
one-
you have infinitely many directions that things can go wrong. Okay? There is one direction in which things go right. You know what? When you go on array. When you go on array, things go nicely because it's a one-dimensional problem. All the other directions, things can go bad. Okay? Despite convexity, despite you have a lot of structure, a lot of beautiful geometry, and you can say lots of things, yes? But still, worst cases are terribly bad.
Is there like a different notion of monotonicity or something for which you can say some better like, results? Like if I can't think of a better notion, but like what can we restrict to so that we can get a positive result? Like,
Positive result, I don't know, but you can talk about different classes of mechanisms. Again, that comes to the by many kind of or super modular or so on. Subadditive, submodular, there are various classes, and you can try to see. Now, most of them will be worse. Do we have any class where we don't have the G4 equals 0? Or for all of them, G4 is 0?
For all of them.
Hmm?
We don't have any notion of monotonicity that does better than the G-reds that you mentioned,
Okay.
right? So all of the classes that we know are worse than
Now, it doesn't mean there doesn't exist one, but we have no clue what it could be. Yeah.
Coming back to economic theory, so this nearly impossibility result which we have reached, that the seller cannot do anything. How did we begin? We began with the unrestricted class of mechanisms, then you restricted it to IC and IR. And then we looked for the best G4 and we found that the best is 0. Suppose I do it a little bit differently. I begin with unrestricted class. I look for the best G4. So say G4, the best is alpha. So each alpha will characterize classes of mechanism. And then now if I impose IC and IR, I'll get restrictions of alpha.
You want to go outside the class of IC and IR mechanisms?
First go out and then...
Now, okay, how do you play such a mechanism? I want to understand. If a mechanism is not IC, what's the meaning of such a mechanism? I mean, the buyer is not going to follow it. So you are not going to get, this is going to be translated into some, buyer is not going to do, you are telling the buyer when his evaluation X to choose that. He's not going to choose it, so what's the meaning of that?
There could be possibility result if you just relax the IR. Maybe the objects which are being sold are vaccinations. It's COVID vaccination, it's mandatory for you to buy. And you have to pay a fee.
Look, if you want to add costs or fees or
Maybe the
that's,
prices which are...
yeah, you can add costs of the goods, you can add entry fee, you can do this modification. I mean, they are not going to change dramatically anything. I mean, they are just going to make a shift of the whole thing. It's not going to solve anything. That's, again, look, that's my conjecture.
Relaxing IR, if I relax IR completely.
Look, IR is like, okay, add a type 00 to the support. You get IR automatically, it's part of IC. It's not, IR is not something that, or you say, okay, IR, the outside option is not 0, it's -7.
Yeah.
So everything shifts by 7. That's not going to change anything. You just add 7 to everything. That's not going to make any difference.
And also IC is kind of without love because you play equilibrium.
And
Direct
exactly,
revelation says
that's a revelation principle.
Yeah.
That's
Yeah.
what you give a game. You look at the equilibrium of the game, and that's what counts.
Exactly.
That's a direct mechanism of the
Exactly.
simple. Yeah. So that's what I said. You cannot go outside.